Good morning, Fancy Meat Computers! Aw, man. Is, 2Q whatever it is your dynamics class making my class look reasonable again? Everybody, okay. Alright. I'm designating the next 2 to 3 minutes for everybody to complain about the midterm that you guys apparently just had to write, and then we're going to get on with the lecture material. So, have at it. I want to hear all the complaints. Primarily because you're not complaining about mine. I mean, if you want to complain about my midterm, that's fair game too, I suppose. 50 minutes for 16 questions. Wow. And like these, correct me if I'm wrong, but this is like, dynamics would be like calculate the velocity of like this piece of the mechanism because it's like at a, you know, it's like this distant from its axle, and it's like, you know, that kind of stuff, right? Like, it involves calculus, right? 2 questions, 16 parts, 50 minutes. Ooh. The work that took about 50 minutes was about 40%. My midterm gave 24 hours, and it needed time, but it was doable. 50, so it's like, what is that? Let me see here. Literally every other midterm just gives at least 90 minutes. Yeah, see, I don't like the in-class midterm because of that, you know? You only have 50 minutes, so, like, what are you gonna do? Do these integrals in 10 seconds or you don't finish? Yeah. 3 minutes per part. Really? Let me see this. 50 minutes divided by 16 parts is... Oh, come on. You had 3.125 minutes per question. Jeez, man. It's like, yeah, but you gotta read the instructions first. Shh. Don't you know that you should be able to read a question instantaneously? Oh, is Dr. Bone teaching it? Oh. Yeah, okay. He's still kicking around, is he? I'm not looking at my work because I need to hope that I did everything right so I actually have a semi-decent mark. Yeah, unfortunately, ignorance isn't bliss, I think. Yeah, I know, Dr. Bone. I did mechatronics, you guys. I did my bachelor's degree in mechatronics engineering. Yes, I know. I had Dr. Bone for a 4th year class. I think I got like a B something, maybe a B minus. I think I got like a 7 in his class. The 0.125 minutes for each question is for submitting it. Yeah. Oh, what, you don't submit all at the end to like be able to batch submit? Yeah. I don't know. Oh, 60% exam? Jeez. Yeah, I passed that class. I passed all my classes. I almost didn't pass thermo. I like what came within like I was within round off error of failing thermo, but yeah. Um yeah. Yeah. Yeah, so when I had thermo, like back in my day, and keep in mind this is like over a decade ago, right? Um, Literally all the Tronies were just like chucked into a chucked into the EngPhys, like a second year EngPhys class. So I passed thermo with uncertainty. Yes. Um, I was terrible. Well, think about my situation, right? Here I am learning mechanics and software, and suddenly I'm expected to do like second year chemistry on like noble gas laws and like thermal coefficients, and like it's just ah yeah, it's terrible. I gave myself a psychosomatic cold when I got my final grade from that. I was like, you know what? Like I actually got physically ill from from a thermo mark. It was psychosomatic though, because I didn't actually have a cold. I just convinced myself I had one. But yeah, I don't know. I guess you can just all you can really do is like pray that he curves it. You know? Yeah. Hmm. See, like my strategy to setting a test is the test should be doable, and then I don't have to curve it. I don't have to worry about curving it. I'm going to have a heart attack on the exam. Well, in that case, I highly recommend loading up on aspirin. Who was my thermo prof? Oh, God. Some guy with a mustache. Uh, oh, my God. Oh, my God. Anyway, so we should actually talk about this class, eh? I allocated 2 to 3 minutes of complaining about Dr. Bones' test, and now we've had 7 minutes. So yeah, um, what if you make the test doable and still curve it? Ah, no. The whole point of making the test doable is so that you don't have to curve it. Um, so, yeah. Um, so, if I may provide some advice to people who may be interested in, like, exams, like deferred exams, keep in mind that deferred examinations are a ginormous pain in the ass for the professor, and so, like I've heard, I don't know, like I can't confirm a specific instance of this in my memory, but I've heard rumors that some profs will do an oral examination as a deferred examination. So, and if I can just say, paper tests suck, right? Oral examinations are like 10 times worse. 10 times worse. If you can avoid having an oral exam, like, avoid it at all costs. What are the deferred exams? Oh, so, like, if, like, you get into a car accident or something the day before an exam, you can appeal, basically it's like the MSAF process, but for an exam, and what they do is they, like, push it off until midterm, like, the midterm break of the next semester. But and it's like your mark is pending until the outcome of the deferred exam, and like in my experience, half the people who apply for deferred exams like just don't write them anyways, because like by that point, what's the point anyway? But but yeah, there is a process like if you fall gravely ill during the exam period, and that's the deferred examination process. But yeah. Anyway, so let's talk data structures. Let's talk data structures. So, so we're going to talk about graph theory. This is probably something that you guys will have never heard of before. But consider this a soft introduction to the type of stuff that you'll probably have to deal with during the data structures and algorithms course that you're going to be taking next semester, right? So some of the notation that you're going to see here is a little bit weird. The concepts are going to be highly mathematical, but just so you know, one of the biggest differences between you and a software engineer is they get a much firmer foundation in the discrete math side of things. You know, basically, while you guys are learning mechanics, they're learning the discrete math that enables them to design algorithms, right? So we're going to give you guys just a little bit of a taste of the type of math that we're talking about here. So, incidentally, do I have the Helmus book around here? I do have the Helmus book around here. Give me 1 second. If you're looking for a compact introduction to the types of stuff we're going to talk about over the next few slides, I highly recommend Naive Set Theory by Paul R. Halmus. They should have this in Thode. I would eat my shirt if they didn't have this in Thode. This is like a text from the 1960s. It's a very classic text on like introduction to set theory and introduction to discrete mathematics. So, you know, if you need to bone up on your set theory, then this is a absolutely fantastic book. Very approachable. The problem that you have with math textbooks a lot of the time is that like they start off like assuming they're talking to like a level 12 mathematician, but you might only be a level 3 mathematician. So there's like the gap is too big to bridge. But this guy starts off talking to level 2 mathematicians. So, and builds you up to a level 12 mathematician. So I highly recommend the Helmus book. It's called Naive Set Theory. If you're interested in discrete mathematics, which, you know, will, like, there's no way that book won't be beneficial to you in 3rd and 4th year if you decide to take my advice. So, there you go. A gift of knowledge I give you. So, anyway. So we're going to talk about graph theory. In order to solve problems, we need mathematical models in which to express these problems. A very useful mathematical model in algorithm design is the graph. So we're not talking about like graphing, you know, x versus y here. It's a very specific definition of graph. Like a graph in discrete mathematics is like a very, very specific thing. The closest concept you should have to it is like a network of nodes, right? So, A graph is a way of modeling the relationships between objects. Mathematically, we define a graph as an ordered pair. So G is equal to a set of vertices combined with a set of edges, where V is the set. So G is equal to V with E. V is the set of nodes or vertices, and E is the set of edges conforming to. So E is a subset of all possible combinations X and Y, where X and Y are elements of the set of vertices, and X does not equal to Y. This condition is sometimes relaxed. That way you can have an edge, like in some types of graphs, you can have an edge that points from one node back to itself. These are known as like self loops. So this condition is sometimes relaxed, but the general idea is that you have a set of points, and an edge is defined by specifying two of the points, right? So the above means that an edge is defined as a pair of vertices where the two vertices may not be the same, although again that condition is sometimes relaxed. So this is a graph, right? So we have a set of vertices, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we have a number of edges. So the edges that we have in this graph are 6, 4, 4, 3, 4, 5, 5, 2, 5, 1, 1, 2, and 2, 3. They're represented down here. The ordering doesn't, like the order in which you specify them doesn't matter. The order in which you specify the edges. So, are you guys following so far? So far, so good. So far, so good. 2 votes. 2 people say yes, so that represents the opinion of the rest of the class, obviously. All right. So, actually 80% isn't a bad hit rate. So, now that we have defined graphs in a very, very general way, we're going to refine our definition of graph with various properties. So basically, graphs are a very, very general structure. You will probably have heard of some types of data structures before. You've probably heard of trees or binary trees. You've heard of trees before, probably. You've heard of lists or linked lists or singly or doubly linked lists. You've heard of those before. Both of those things are graphs with different properties applied. So let's discuss some of the properties that you can have. So, directed graphs. The previous 2 slides represent graphs in their most general form. If we apply properties to graphs, we get some interesting structures. Directed graphs. If the ordering of the numbers is in an edge pair matters, the graph is directed. Simply put, the graph has arrows instead of straight lines. So, you know, if 4, 3 and 3, 4 are equivalent, right, then this is just a line. But if 4, 3 means go from 4 to 3 but not back again, then this means that it's an arrow, not an edge, which basically turns it into one of these. So now that we have an idea of directedness, we can start reasoning about those directions. So we also identify the difference between cyclic and acyclic graphs. So a cyclic graph contains cycles, and an acyclic graph does not contain cycles. A cycle is defined as when you have it in a graph so that you can return to a node by following the edges of a directed graph, that's known as a cycle, right? So, for example, this guy on the left, this is cyclic, because if you take this node here, for example, you can follow the arrows back to it. Cyclic. So a graph only needs to contain one cycle to be considered cyclic. An acyclic graph, on the other hand, you'll notice there are lots of arrows going on here, but they're all kind of pointing down, and it's like if we start at 3, we can go to 8, and then we can go to 9, but there's no way to return to 3. And that's true of any node here, right? If you start at 11, you can only go to 2, 9, or 10, and there's no way to get back to 11. That makes it a... this makes it a directed acyclic graph. Graphs have a lot more properties than this, but this will do for now. So you may be saying to yourself, okay, sure, but why? Why are you telling me this? How could this possibly be relevant to one of the lowest level languages in existence, which is the C programming language? So, the question becomes, how can we take this type of structure and build it into C? And given that this is the lecture on structures, you might imagine that structures have something to do with it. So, in the context of C programming, we can make... I'm sorry. I'm terribly sorry. I had a hair in my mouth. That's what you get with. That's what you get for living in a house with 4 other animals, 2 of which are cats and shed. I'm pretty sure it wasn't one of mine. Anyway, so nodes can be represented with structures in C. Edges can be represented with pointers. So if a structure contains a pointer to another structure, that makes it an edge in a graph. So let's talk about singly linked lists. Talking about linked lists in the context of C programming is like, this is about as classic lecture material for a C course as you can possibly get. Like, they have been teaching linked lists in C classes since like probably since the 80s. So anyway, you know, as soon as they started teaching classes on C, they started talking about linked lists. So, a singly linked list is a graph where each node points to one other node, or no nodes, and no node is pointed to more than once. So we have a directed acyclic graph where each of the nodes points to at most one other node, right? And no node is pointed to more than once. This effectively creates a linear data structure. So you'll notice each one of these nodes points to one other node, or 0 other nodes. The end one points to 0 other nodes, and none of these are pointed to more than once. This is similar in many respects to our old friend the array, but with some key differences. Singly linked lists are actually how some fairly popular programming languages, such as Lisp and Haskell, store their lists natively. So their native primary aggregate data type is stored in this manner. So they use pointers in like right in at the level of it's embedded in the syntax. Lists in Python will probably be doing something similar, although I haven't. I don't know that much about the substructure of Python to be able to tell you that for sure. So, linked lists with structures. The nodes of the graph can be expressed as objects of a structure type in C. all we need to do is taking an existing structure and add a self-referential pointer next. So this will really bake your noodles. So you remember our pinball high score table structure, right? All we have to do is add SLL node next. Well, I guess we renamed it from customer to SLL node, which stands for singly linked list node. We add a pointer to the next one, and this is now a singly linked list node. Well, okay. It's not just in how you define it, it's also in how you use it. But, you know, we're getting there. So the last element in the list will point to null, right? So the last element in the list will have a pointer that points to nothing. Every other element in the list will point to the next thing in the list, right? If we wish to refer to a singly linked list in main, or one of our functions, we only need a single node from which we can access the rest. So rather than passing around an entire array, all you have to pass around with a singly linked list is you need to pass around the first node in the list, right? Because the list contains, you know, sequential references to all other nodes in the list, you don't need to include them all in the list. You can just give it the head, and it can figure out the tail. Make sense? So far, so good. You guys done linked lists before? Maybe? So, to visualize. If we apply our data structure to the singly linked list structure, we get the following. For those of you who are beginning to struggle with the material, I can't help you unless you ask a question. I don't know. I can't just read your mind and say, "Oh, this person doesn't understand that." I need you to ask me a question. Formulating the question is half of finding the response. So, if we apply our data structure to the singly linked list, we get the following. So basically, we're representing each of our data structures as this kind of node that contains fields, right? Name, email, and pinball. And each one contains a pointer to the next one. Pointer to the next one, pointer to the next one, pointer to the next one, and then the last one points to null. Can you code an example of linking lists with structures? Yeah. Let me just finish the slide. Do I have like an implementation here? No. Okay. All right. Yeah, we can do one. The more information that is contained in the structure, the more advantageous it is to organize it in this manner. If you want to pass the first node by reference to a function, keep in mind that within the function, you will have to dereference the argument to get to the first node's data. So, to some extent, doing an implementation of this might be the subject of a future assignment question. So, you know, just so you know, that's going to feature reasonably prominently in the assignment 5 material. Yeah, let's just take a look-see. Singly linked list .c. Good. So, include stdio.h. Struct SLL. We'll just call it that. Forgetting my syntax for a moment. Syntax. Let's just do it in simply. Let's say int val. So all it's doing is holding a single integer value. Is assignment 4 going to be out tomorrow? Ooh. Yeah, assignment 3 was just due, eh? So assignment 4 should be out. Yeah. Let me write that down. Good. All right. So then we have a pointer to a structure. So SLL star next. Right? So int main so a way that you should do this, I would say, well, first of all, let's say type def struct SLL, so capitalize it, SLL pointer head, that'll be the head of the list, and let's just initialize it, malloc size of SLL, capital, there we go. So that creates space in memory for the head of the list, right? So we can say head value is equal to 1. Why not? Head next is equal to malloc size of SLL. So we're allocating the next node, storing the pointer in next. Head next value is equal to 2. All I'm doing here is I'm demonstrating to you the basic operations. I'm not putting this in functions or anything. This is just like basic access of stuff, right? So head next is equal to malloc size of SLL, etc., etc., right? Head next val is equal to 3. And so you can, printf, for example, head next val. For example, let's see if this compiles. Ah! Struct SFL. That might be an error in the slide, actually. That takes care. See what I'm saying? Start with the first error in the list. Start with the first error in the list. Declaration of malloc. Oh, yeah, okay. Include stdlib.h, of course. Try again. Ah! No compiler errors. Wah, wah, wah. What does struct SLL mean? Struct SLL, you declare a structure data, you declare a structure, you give it the name SLL, right? So basically, before I hit this type def, I need to basically, the way that it works in C is that similarly to how you attach the tag unsigned to an integer to make it an unsigned integer, you attach the tag structure to like some customly defined data type in order to make it a structured data type. The correct way to think about SLL is as a data type because you use it in places where you would use a data type, right? And it's like a customized data type. So that's why you use struct SLL here. What this typedef does is it renames struct SLL as just SLL in capitals, right? So there you go. Can I briefly go over the lines of code and what it does briefly? Yes. But first, let me run it to make sure that it actually does work. It doesn't hit a seg fault. Aha! 2. It does work. Right. There we go. So, each line of code. Here we go. Hold on to your butts. So, include standard IO. Include standard library. Declare structure, SLL. Include in structure SLL integer value. Include in structure SLL. Pointer to another structure, SLL. Redefine this guy as that guy for convenience. Start main function. Declare pointer to singly linked list node called head. Allocate memory the size of one singly linked list node to head. Take head value, follow to so take head, dereference it, take the value field, assign 1. Assign to the next field of head the pointer returned by malloking another size, another singly linked list node size of memory, right? Then head next value is 2. Head next pointer, allocate another node. Head next value, 3. There you go. I'm not freeing these, by the way. Freeing it would be like head, so free head next. Just like deconstruct it in reverse order. There. So does that mean struct SLL next is referencing a pointer with the typing of struct SLL? Yes, that's it. Struct SLL next is a pointer to something of type struct SLL. That makes it a self-referential pointer because it is referencing something that is the same type of the thing that it's in. Good. What does arrow do again? It's field access combined with pointer dereferencing. So head is a pointer, right? So to get at value, you need to dereference the pointer. This is an equivalent operation to, for example, dereference the head. Dereference the head. That's the same thing as arrow. Dereference the head, take that field. Is SLL calling himself from his stomach? Yeah, that's one way of saying it, I guess. Should you have freed the pointers at the end? Yes. Value is not as in the variable value, as in the litter's meaning. I don't know what that means. Literal meaning. No, yeah, it's val, right? It's just a variable. It's just a field of the structure. So is struct SLL at the beginning defining the structure, not an actual object with the structure? Yeah, so if you want to put it in, like, object-oriented language, um, this just declares the memory space for it. This initializes the value with it, so you could think of, like, this line as being the constructor, you know? But, C is not an object-oriented language. Is head a pointer that's pointing to an undefined structure that can be accessed and changed, change any value? Let me read that again. Is head a pointer that points... So it comes down to the way that C uses structures, right? Basically, C uses structures in the same way that Python uses a dictionary, except in C, the way that it works, roughly speaking, is when you access a particular field of a structure, C knows where it is in the structure and how many bytes it has for size. That's the information that you're giving here. Is like ordering inside of the structure memory space and number of bytes. Uh-oh, have I been lost? Hello, am I still coming through? Yeah. Yeah. So... what was I saying? So if you imagine like the memory space that's allocated to the structure as being sort of blank, it's kind of a structure because C uses it like a structure. You know, it's like I'm putting the data in this particular offset. If I know to retrieve it from the same offset, which is done by calling the same field or invoking the same field, then it's used as a structure and everything is fine. What does the .val in dereference head.val do? Like, why do you need it? So, because that's the field you're accessing, right? It's like you can't, like, for example, if I were to not do something with a pointer, if I were to just have, like, some SLL node, you know, x, right? If I said x.val that and set it to 4, I could say, you know, printf x.val. That would be fine. That's the normal way of accessing a structure when it's not a pointer. If it's a pointer, you need to dereference the pointer first, which is why this happens. Okay, good. So, good. How would you access head next val with the pointer dereferencing way of doing it? Oh, that's not too difficult. You would do, I believe, this would work. It would be head.next dereference. Take that .next and dereference, and then that .val. I'm pretty sure that I may have messed up the parentheses, but yeah. Maybe this works. Yeah. Yeah, there you go. That's how you do it. But, you know, you can see how arrows are easier. You didn't learn dictionaries. Oh, you should learn dictionaries. Dictionaries are super, super useful in Python. So do all structures in the linked list have to have the same amount of data in them? Like they all only have val? Yes, correct. So the structure of the node itself is statically defined. Yeah. That being said, if you want to like if you want to throw some extra fields in them in there and just not use them for some of the nodes, you can totally do that. But the memory has to be allocated from them. We have to know how big the nodes are to be able to allocate the memory for them. Yeah. Instead of dereferenced head.val, could you put head arrow val? Yes, that's the whole point I'm trying to make, is that they are equivalent representations. Yes. Like, if I were to put an extra next in here, you'll see that these two print statements say the same thing. See? They both point to 3. Ta-da! So if you want to print, like, the 10th value of the list, would you just have to have a long chain of, like, next, 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 next? Well, you could do it that way. Or you could write a loop to do it. So this is how you traverse a linked list, right? So let's say you had, like, let's say you wanted to find the last element in a linked list, right? So you would declare some SLL pointer traverse, and you would say, you would initialize it, traverse is equal to head, while traverse dot next is not equal to null. First, we'll print the value of the node we're currently on, traverse dot val, just to prove that it's working. And then traverse is equal to traverse dot next. I'm going to have to dereference. Dereference, dereference, dereference. There we go. Good. This should work. If I just pulled myself out of Python thoughts for one moment. All right. GCC. Aha. Not quite what I wanted, hey? Let me see. What am I doing wrong here? Well, at any rate, it would take me some time to debug it. Did I assign null to any next? Ah, there's a good one. That's a good question. I should really assign null to the last next in the... There we go. Good catch. Is it because I freed them already? Ha! Yes, that would do it. Yeah. Why don't you try traversing a list that you just deleted one line ahead? And they let me teach classes. Alright, there you go. So the list works. Right? So this stops when the next one is null. So if you want the last one, you have to, like, put this line down here as well. But, there we go. See, it prints out each one in turn. So no, you don't have to just do, like, very long chains of next, 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 next. Actually, technically speaking, these types of algorithms are built for recursion. So you can do this with a loop reasonably easily, but you can also, like, you can find an element in a list by like you can find the end of a linked list. Basically, if you chop the head off of a linked list, the thing that you get as a result is another linked list, right? So, like, take this, right? If I say, I'm just going to consider 1 to be the new head, and you perform the same operation, it's like, I didn't find what I wanted. Let's consider 2 to be the new head, and see if I can find what I wanted. Like, that's what a search operation would look like over a linked list, right? Yeah. Yeah. That's how Prof. Moore was laughing when he saw the exam submission. Can neither confirm nor deny. Actually, I kind of like auto-grading systems because I don't really see it unless there's a problem, you know? I'm perfectly content to allow the computer to do the marking. To be completely honest with you, like, good lord, like, the third-year class that I'm teaching this semester, like, the material is not really, like, a lot of the material there is, like, writing proofs, which is not something that you can auto-grade, because, like, they're not writing code, right? They're producing mathematical arguments, and you can't auto-grade those, really. So, essentially, I've been relying on smelly humans. Not that they're particularly smelly humans, just, you know, humans in general smell. That's one of their properties. But I've been relying on humans to do the grading, and it's like, I'm used to teaching classes where it's people that do or where it's a computer that does the grading, and like, holy heck, is it like a pain in the ass when like humans are just I hate humans so much. Well, I don't hate them, but I hate it. I hate that they aren't computers sometimes. Anyway, yeah. Write an AI to do the marking for me. Well, I mean, it depends on what you consider artificial intelligence. Does arrow only work for structure pointers, or if I had an array, could I do pointer 6 to get the 6th value of the index? No, it doesn't work on arrays. It only works on structures. And it's because of, like, in that particular instance, David, it would consider 6 to be a string, right? It would consider it to be a field name, which arrays don't have field names, so that would be a syntax error. But yeah. Anyway, so it's class overtime. If you have any further questions, please let me know. Otherwise we'll just end and get out of here. I have to trace through the thing and listen back to that laugh that everybody's talking about. How long ago was that? Yeah, that's a pretty good laugh. Somebody clip that for a meme compilation. Quick question about the midterm. If there was a problem with our submission, will we be notified? Awesome. If there's a problem with the submission, if you're concerned about it, email Chev. Chev's on the case. probably it's fine. It's probably just nerves, you know? But yeah. Anywho, all right. I'll take my leave here. Stay in a state that is not yeah, whatever. How do you clip on YouTube? OBS. Yeah, OBS is everything. OBS is the god of live streaming. Cool. Take it easy, folks.